And we're back. So, like I said at the end of the last one, sometimes we can find integrals just by using geometry and not even using any calculus, so to speak. Exactly. I mean, knowing that taking an integral is the area between the curve and the x-axis is calculus, but sometimes the calculation of that area can be just done with geometry. So here's an example. I'm like, calculate the following integral. I don't know what the hell that thing is. Like, I don't know what that looks like. So sometimes you think about what the shape of the integrand is. Like, what does this function represent? So let's say we say that this is y. This is some function f of x, or we can, since we often do, we call y the same as f of x. We can say, let's say this thing is equal to y. All right, so y equals that thing. And then I'm going to square both sides of this. So I do y squared. And the square root of something squared is just the something. So that becomes 16 minus x squared. And I can add the x squared to both sides. There's a reason why I'm doing that. I get x squared plus y squared equals 16. And so it turns out, if you remember from our conic sections unit at the end of pre-cal, this is the equation of a circle centered at the origin with a radius of 4. It's like x minus h squared plus y minus k squared equals r squared. That was our formula. In this case, h and k, which are the coordinates of the center, are 0 and 0, thus centered at the origin. And r squared is 16, so r is 4. So basically, this thing is this integrand here is a circle centered at the origin with radius 4. So like that, maybe. Which is great, but like, if I think about the area between the curve and the axis, like what about the bottom part? Is it like positive and negative or something? Or do I add these up, or what happens? And what happens is that what we actually maybe didn't realize is that when we squared this, we like kind of destroyed the fact that this is a positive piece. Really, this square root of 16 minus x squared is just the top half of this circle. Like this part down here is not really there. So really what I want is just like this thing. Yikes. Let me see if I can do a little better. That part's good. That part's pretty good. That's just going to have to do. What I really want is just that. So basically, this curve right here is y equals the square root of 16 minus x squared. That part on the bottom, which I just got rid of, is y equals negative root 16 minus x squared. But I don't care about that because it said to find the positive one. Well, so this is half of, so this area here is half of a circle. I know how to find the area of a circle. The area of a circle is pi r squared. So the area of my thing, I'm going to write it a little more officially. I know that the definite integral is equal, this definite integral is equal to the area here. So I can say the integral from -4 to 4, square root of 16 minus x squared dx is 1/2 of a pi r squared, where r is the radius of this circle. Since that circle has a radius of 4, it's 1/2 times pi times 4 squared, which is 8 pi. 1/2 of 16 pi is 8 pi. So if this integral had said from 0 to 4, I would have just wanted like this quarter of a circle here, and I would have done 1/4. Maybe if it said from -4 to 0, that would have been from here to here. Like these limits here tell you which x to start at and which x to end at. This one said -4 to 4, so it's the entire half circle. So there, I used geometry to find an integral. I got the answer, it's 8 pi. That's exactly the area underneath this curve. Okay, what if the function is a constant though? A constant. Right. So this is like, I think about that as a function. It's like the function y equals c. And y equals a number, a constant, is always just a horizontal line starting at c. So this is what my function looks like. Now I'm just going to pick some arbitrary a and arbitrary b. I'll draw the curve in a different color so that we can distinguish it from everything else. And then from a to b, it's the only place that I'm actually interested in here, right? The integral from a to b of c. It's this area right here, which, if I'm not mistaken, is just a rectangle. The height of the rectangle is c. And the distance from here to here is b minus a. Like if it's like from 2 to 8, then this is clearly 6. If it's like from 0 to 11, it's clearly 11. And you could think about if if this a was negative or they were both negative, if it would still work, and I promise you that it does. So basically the height of my rectangle is c, the width is b minus a. So the integral, which is the area, is just height times width, or base times height, or whatever you want to call it. So for example, if my constant is 13 halves, this integral is 13 halves. That's like the height of the curve, so to speak. And then I do the top limit minus the bottom limit. 5 minus negative 3. There's only 5 plus 3, which is really 8. 13 over 2 times 8. 8 divided by 2 is 4. 4 times 13 is 52. So there's another way we could do this integral. If we're remembering that the integral is the area between the curve and the x-axis. Here, that area was a semicircle. Here, that area was a rectangle. Both of those are things whose areas I know how to find. Right. So what if, like, everyone we've seen so far, like the bottom limit has been smaller than the top one? That was true here, right? And like we think of this as the left side and that's the right side. But like, what if I switch them? What if the one on top is smaller than the one on the bottom? What that means is you do the negative of the integral from a to b. We're going to see an example of this in a minute, which might help to explain this. But when I switch the limits of integration, I change it from, I take the net, like the area becomes the negative of what I wanted. Some people think of it like, when you go from b to a, the dx is negative, because instead of going like a bunch of little dx's like this, I'm doing a bunch of dx's like this. So it's like the heights are still positive, but the dx's are negative. That's the way to think about it. There's a million ways to think about it, but that one, some people have mentioned to me in the past. So. Additivity, okay, so let's say I have a to c now, and there's a b in the middle. So like I have some curve that looks like this or whatever. And like, basically this is saying you can split up these intervals if you want to, and you just add the pieces together. Like this, the area here, let's say this curve is called f of x. This area right here is the integral from a to b of f of x dx. This area right here is just from b to c now. The integral from b to c of f of x dx. And it's fairly clear to me at least that if I want to find the whole area between the curve and f of x from a to c, I add up this area and this area, which means I do the integral from a to b of f of x dx plus the integral from b to c of f of x dx. And like the trick is that the b here and the b here match. So it's like I go from a to b and I stop for this one, and then I go from b to c for this one. And I get all of the pieces because I stopped at b and I started at b. So that's just going to be like a little thing so that if you have more than one shape in a piece, you can add them together and get the whole answer. So, and this is kind of the last little piece of, is it? Yeah. This is like the last little piece of theory, which says, definite integral defines the area between the x-axis and the curve when it's positive. But when the curve is above the axis the whole time, the integral is just this area. You just find the area somehow, and this is what the integral is equal to. But a reasonable question would be, what happens if the curve goes below the axis? And the answer is, what happens is, let's say the area here is A and the area here is B. The integral treats area below the axis like it's negative area. It doesn't really make any sense. This is like, what the hell does this even mean, right? Negative area. It's like not like a concept that we have like a good like understanding of. It basically just means that the integral, like let's say that this area here, let's say this area here was 5, this area here was 4. Then the integral, I don't know, let's say that this is 0 and this is 10 or something. The integral from 0 to 10 of that curve is going to be this and this, but this counts as negative. So you'd say something like -5 plus 4 equals -1. Basically, any area that appears between the curve and the x-axis when the curve is below the x-axis is negative. Like I said before about when you switch the limits of integration, like the dx's are negative, some people think of this part like that the f of x's are negative. And so like when I do a negative number times a positive number for the dx's, I get a negative area. Remember, this area is always like the sum of a bunch of rectangles. So like up here, this is the f of x's all look like this. It's greater than 0. And the delta x, which is right here, is also greater than 0. And so a positive number times a positive number gives me a positive piece of the area. But for these ones, the f of x's are negative, right? Like this is a negative number. So I do a negative times the positive delta x and I get a negative area. Again, negative area is like a weird thing to say. Doesn't really feel right to say it out loud, but that's basically what's happening. Here's an example, a more concrete example. So calculate the following integral. Here's a picture of it so you can see what's happening. The integral from 0 to 5, x equals 0 to x equals 5, of the function 3 minus x, this is the graph of the function 3 minus x dx. So I can find areas pretty easily because these are right triangles. There's a right triangle and there's a right triangle. So the area here is 1/2 times the base, which is 3, times the height, which is also 3. So that's 9 times 1/2, it's 9/2. And the area here, do it the same way. 1/2 times 2 times 2, and that is 1/2 of 4 is 2. But to find this integral, I got to pay attention to the fact that this 2 is really made up of a bunch of negative f of x's times delta x's. So this area is 2, but the integral will treat that area as though it is negative. So this will be 9/2 minus 2. This is the important thing here. It's negative. And 9/2 is positive because this region here, with the area of 9/2 is above the x-axis. This region here with the area of 2 is below the x-axis. So the integral treats it as negative. And so I get my integral. The integral would return 5/2. That's the value of this integral, is 5/2. All right. Last thing. So these things are integrable. Okay, so this is just some kind of notes. If I have the integral of 2 things added, I can take the integral of each one separately and add those together. The integral of a sum is the sum of the integrals. And if there's a constant multiplied by a function inside an integral, I can pull the constant to the outside. Just thinking hop to the outside. It's basically you can factor a constant outside of the integral. Sometimes this is easier to take the integral of than with the constant multiplied by it. That's the reason you might do that. These are the kind of things that you guys will like freak out about trying to memorize, and you'll use them without even thinking about it all the time. So I don't recommend memorizing them. It's just for the sake of completion. I thought I'd throw them in there. So we will do plenty of practice with this in class, I promise. Okay, bye.